So what I want to talk to you about today are electron configurations and more importantly how to write them. So before we do that, we need to understand a couple of things that are really important. One, we always want to put electrons in the lowest possible orbital that's available. That actually has a specific name. It's called the Aufbau principle. You will need to know that down the road, but for right now, you need to be aware that given a choice, if we have a higher energy orbital or a lower energy orbital, electrons will always go to the lower energy orbital. Second thing you need to be aware of is something called Hund's rule. Now we talked about this before, but Hund's rule says whenever you have a set of orbitals that are of equal energy, you put one electron in each orbital before you put two in any. If I can remind you of this, let's say we have a set of p orbitals, which p orbitals always come in a set of 3. We would put one electron in each orbital before we put a second electron in each orbital. The example I gave you was the Christmas analogy, whereas you don't want to have each of your siblings getting multiple gifts and you getting none. So those are two very important rules to start off with. The other thing you need to be aware of is that atoms have 7 main energy levels. So before when we learned about Bohr, we said that there are 7 orbits around an atom. We're going to be a little more specific this time. We're going to say there's 7 main energy levels. There are sub-levels, and the closer you are to the nucleus, the less energy you have. So given a choice, you're going to want to put your electrons in the first energy level versus the 7th energy level. The other thing that's really important is that no matter which orbital, no matter how complex or how simple or how large or how small your orbital is, the maximum number of electrons in any one orbital is just 2. Now, let's go through the different shaped orbitals. These are things that we know we've seen before. The s orbital is the most simplistic orbital. It literally looks like a sphere, and s orbitals always come in sets of 1. In other words, you only have one shape of s orbital. P orbitals, they're a little more complex, and they always come in sets of 3. Now I can number these for you, but you can probably count them out yourself. There are 3 different p orbitals. So whenever we're talking about p orbitals, we need to reflect or refer to which one of these 3 orbitals you are in. D orbitals, they look way more complex, and I just want to refer you to this guy over on the far side. This is crazy looking guy. I guess I'm off the screen right there. This guy right here, it looks like a donut in between around a stick. These 5 different shaped orbitals are all in existence whenever we talk about d orbitals. Now, if you can put 2 electrons per orbital, that means that in all of these combined, in a set of d orbitals, we can put in 10 electrons. The f orbitals, these are the most complex, and they're crazy if you take a look at even how they're annotated. Take a look at this. Fz cubed minus 3/5 zr squared to get this weirdish looking blobbish thing. Again, electrons live inside these spaces right here and here. So the 4 orbitals that we need to be aware of are s, p, d's, and f's, and that'll allow us to then put electrons into these orbitals. Now, how do we put electrons in the lowest energy orbitals? Well, we follow these arrows. Now, if you take a look here, this is something that's going to be with us at all times. If we follow the arrow from tail to head, it fills the orbitals up from lowest energy to highest. So the first orbital we'd run through, wouldn't it be the 1s? And then once we get through the 1s, wouldn't we have the 2s? And then after the 2s, wouldn't we hit a set of 2p orbitals? And this is how we're going to track where we put electrons in orbitals. So one of the ways that we can show people where electrons are in atoms is with orbital notation. Now, how does orbital notation work? Well, the best way to do it is with an example. So let's pretend that we have 22 electrons. Now, what we're going to do is we're going to follow the arrows in the diagram on the up here, and we're going to put electrons into the orbitals based on how we follow the arrows. So if you look at the very first arrow that we're following through, do you see how it follows through the 1s orbital? So what we do is we write 1s, and then we put a little line above the top of it here. Now, above that, we put in however many electrons that can fit into this orbital. And the way we do that is by drawing arrows. One goes up, and one goes down. Now these are little half arrows, but each one of these arrows represents an electron. So of the 22 electrons, I have placed 2 electrons in this first 1s orbital. That means I still have 20 electrons left to place. So if I keep on going, after the 1s, I run into the 2s. And again, we're looking at this diagram right here in the upper corner. So after the 1s, which we just put electrons in, we have the 2s. So similarly, we're going to write a 2s, and then we're going to put the number of electrons that we have into this orbital. So we're going to put, again, 2 electrons into here. Why? Because we know we have 22 electrons we have to put into orbitals. We're going to fill up as many orbitals as we can until we get to the 22 electrons. So here I have 2 electrons on the 1s, 2 electrons on the 2s, which means I've placed 4 out of the 22 into orbitals. Now after the 2s orbital, I hit the 2p orbital right here. And again, we're following the arrows from left to right. But 2p orbitals are unique because p orbitals come in a set of 3. So when you're doing the orbital notation, you actually have to draw all 3 of these orbitals in. Now, I want to make a note of this, and this is really important. The 2 right here, it only tells us that we have a set of p orbitals at the second energy level. It doesn't tell us that we have 2 p orbitals. It tells us that we have a set of 3 different p orbitals at the second energy level. The other thing I want you to be aware of is this. When we put electrons into a set of orbitals that is the same energy, we always put 1 electron in each before we put 2 in any of them. That's what Hund's rule says. So here we put 1, 2, 3, and then we're going to go 4, 5, 6. So altogether we've placed 10 electrons in of the 22. Where do we go to after the 2p? Well, we go to the 3s. We can put in 2 in there. After the 3s, we go to the 3p. Again, p orbitals come in a set of 3, except this time the p orbitals are at the third energy level. Again, we're able to go 1, 2, 3, 4, 5, 6. Now altogether, if we add up the electrons, and if you ever lose count, you can just count them in pairs. You can go 2, 4, 6, 8, 10, 12, 14, 16, 18. We've placed 18 of the 22, but here's where it gets tricky. See, after the 3p orbital, if you follow the arrow through in this direction, see how it goes to 4s and not to the 3d? And that confuses some of us because we like the idea to be, well, we put everything in the first energy level, then the second energy level, then the third, and then the fourth, etc., all the way down to 7. But what ends up happening is that this 4s orbital actually has less energy than the 3d orbital. So when we're putting electrons into orbitals, we go into the 4s before we go into the 3d. The example I gave in class was, yes, as a whole, fourth graders are bigger and stronger and faster than third graders. But it's entirely possible for a single third grader, and in this case my 3d orbital is my third grader, actually would be stronger or faster than the weakest of the fourth graders. So in terms of orbitals, the 4s actually has less energy than the 3d, which means that we put electrons into the 4s before we put electrons into the 3d. So right now we've put 20 of our 22 electrons in. We've filled up our 4s. Now we go to the 3d. And the thing with the 3d is that there are 5 orbitals in a set of 3d orbitals. So we have to actually draw them all out when we do this. Now, if you do the math, up to this point, we've placed 20 electrons into orbitals. We're only lacking 2 more. That means in this set, this entire set right here, we can only put 2 electrons in. So in order to follow the rules, we put 1 electron in the first one and 1 electron in the second. That's according to Hund's rule. We would not put 2 in this one here. So we go 1, 2, and we're done. So this right here represents 22 electrons being placed. That's a significant number of electrons, but not unmanageable. What if we wanted to do 35 electrons? Well, let's try that. This time we're going to go with 35 electrons, which is a whole heck of a lot more. And when we do this, we're going to follow the same order that we did before, and we're going to be following the arrows as we move through each one of these. So the first one is going to be the 1s. So I'm going to put my little drawing, 1s. I'm going to put 2 electrons in here. Well, it got really sloppy. Then I go to the 2s. I'm going to put 2 electrons in here. Again, if you're wondering what we're doing, we're just following the orbitals along. My 2p's, my p orbitals always come in a set of 3. So I'm going to go 2p, 2p, and 2p. And since I know that I have 35 electrons, I'm easily going to fill all of these orbitals. I'm going to do so like this, and I place 10 electrons in. After the 2p comes the 3s, and with the 3s, I can put 2 electrons in. Then after the 3s comes the 3p. Again, there are 3 p orbitals always in a set. Again, I'm filling up these orbitals, so I'm going to put one in each one and a second one in each one. After the 3p orbitals, here comes the controversial 4s, which is actually less energy than a set of 3ds. And I'm going to draw my 3ds. 1, 2, 3, 4, 5. They're going to get progressively smaller, and I didn't want to write 3d out a bunch of times, so I'm going to write it like this. But each one of these orbitals is completely full. So I'm going to put one in each one and then go back and put a second one in each one. And if I did the math on this here, I've only put in 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. That means I still have to put 5 more electrons into these orbitals. So after my set of 3ds, if you follow, here's where I'm at. I'm at 3d. Then I'm going to go to 4p. Well, 4p orbitals, since they're p orbitals, they come in a set of 3. So if they come in a set of 3, I'm going to draw them out. 4p, 4p, and 4p. I have 5 electrons left to place. So when I place them, I'm going to go 1, 2, 3, and then go back and go 4, 5. This is the last electron we placed, not this one right here. Now, 35 electrons is kind of painful to do orbital notation for all 35 of them, but what if I wanted to ask you to do 80 or 100? This would get old really, really fast. So there's a quicker way of doing that, and we call it electron configuration notation. Now, I'm going to show you this here. It's called electron configuration notation, but then I'm going to go back to the previous page because it'll make it easier to track how the electron configuration notation is quicker. So we're going to go back to this, and here's how we do it with electron configuration. What we do is instead of drawing out every single individual orbital, we group orbitals in sets. So I'm going to do these 35 electrons right here with electron configuration. So what we do is we write the orbital, and then the number of electrons in that orbital we write as a exponent. So here it's going to be 1s, and because there's 2 electrons right here, we write 1s2. The next orbitals we're putting into are the 2s. So we write 2s, and we can put 2 electrons max in here. Then if you take a look here, we have 6 electrons in the 2p. But instead of having to write out every single orbital, we write 2p, and then we go 6. Similar, as we move on, we're going to go one after another. We're going to write 3s2, 3p 6, 4s 2, 3d 10, and then 4p. And here's where it's important. We only put 5 electrons into these p orbitals, so we have to write it as 4p 5. Now this is clearly easier to write than all of this up above. But even still, it could be problematic if we had to write 80 or 90 electrons. So the next video, I'm going to show you how to do shorthand notation. Hopefully this is